Hey math friends, here is our last section of notes for AP Calculus for this year. This is section 7.5. So in the last section, 7.4, we were working on finding general and particular solutions to differential equations. And section 7.5 is really just an application of that. This is one special case of a differential equation that would be of either an exponential growth or an exponential decay model. So let's assume that we begin with a differential equation of the form dy dx equals r times y, where r is some constant of proportionality. This equation says that the rate of change of y with respect to x is proportional to y. If we are given an initial condition, like y of 0 equals p, we can use this information to find the particular solution, y equals f of x, to this differential equation. So basically, the steps that we are about to take are exactly what we were doing in section 7.4. All right, so I'm going to begin with step 1, which is going to be to separate. So if I have dy divided by dx equals r times y, I am going to move the y under the dy. And that is going to be equal to r times dx. Then step 2 is going to be to integrate both sides with respect to the variable on that side. So integrate with respect to y on the left, integrate with respect to x on the right. So the integral of dy over y. And actually, I'm going to backtrack for a second. I'm going to write that as 1 over y dy is equal to the integral of r dx. Okay, so when I integrate the left, the integral of 1 over y, or the antiderivative of 1 over y, is ln of the natural log of y. And remember, we'd have a plus c, but we combine both of our constants on the right side. And the antiderivative of this side, really that r is a constant term, so that would come in front of the integral. So it's really the integral of 1 dx, which is going to give us rx plus c. All right, then our step 3 is going to be to find our c, right? And we're using our initial condition, which is our point when x is 0, y is p. That was our given initial condition right there. So when we plug that in, we get natural log of p is equal to r times 0 plus c. Well, r times 0, that's just going to be 0. So we get that c is equal to the natural log of p, okay? And, oops, in this case, I kept the absolute value bars there around my p, but keeping in mind that, when we're talking about an initial condition, the initial condition of an exponential growth or exponential decay model would be the quantity that you're starting with. So this p is really going to be some positive value because it is the amount we start with. And obviously we can't begin with a negative quantity of anything, right? So at this point in time, I'm just going to say c is really just equal to the natural log of p. All right, so step 4 is going to be to plug our c into our equation from right here, right? So now we have natural log of y, absolute value of y, is equal to rx plus natural log of p. And again, we drop those absolute value bars around the p because we know if p is our initial amount, it has to be a positive value. Okay, so now step 5 is going to be to solve for y. Well, if my y is trapped inside of that natural log, then I am going to need to get it out of there by using a base of e on both sides. So I'm going to have e to the natural log of y is equal to e to the Rx plus natural log of P. All right, so on the left-hand side, the E and the ln undo, right? So I end up with absolute value of y is equal to. Now on the right side, I'm actually going to think about my exponent rules in reverse. If I've got e to the rx plus ln p, I can say that that's really e to the rx times e to the ln p. And the reason that I want to do that is because the e to the ln p, that can be simplified. E raised to the power of natural log of p, the e and the ln just cancel out, and that's just p, right? So really, I can write this as the absolute value of y is equal to p times e to the rx power. Okay, but again, now that we've gotten to this point in the problem, we can go ahead and we can drop those absolute value bars, because once again, if we put a plus or minus on the other side, that wouldn't really make any sense, because we already discussed the fact that our p, or our initial value, is a positive value. So we're going to say y is equal to p times e to the rx power. So I want you to notice that the solution here to our differential equation back here with our initial value right there, this relationship, it's always going to be the same. Okay, if you start with dy dx is equal to some constant of proportionality, whatever they call it, times y with an initial value of y of 0 equals something, your solution to that differential is always going to be a function that looks like exponential growth or exponential decay. It's always going to be y equals your initial value, right? Because this was your p right here. This was your initial value, times e to the rx power, where r was that coefficient of the y in the differential. So the next page here just kind of illustrates this rule, the relationship between the differential and our solution. Our solution is what we're used to seeing as a form of exponential growth and decay models. Once we recognize a differential equation as being a rate of change of an exponential function, we can shortcut backwards to our solution. So basically what that means is the work that we just did in the previous screen, as long as you remember that relationship, you get to skip that work, okay? You get to take this and go right to that, because we just proved that that relationship is always going to be the case. So let's take a look at the first example. It says, during optimal conditions, the rate of change of the population of a certain organism is proportional to the population at time t in hours. At time t equals 0 hours, the population is 300. So right there, that's our initial condition. Let's write that down. At time t equals 24 hours, the population is 1,000. And we also have, so this is like another ordered pair. At time t equals 24 hours, the population is 1,000. At what time t, that's the question, right, is the population 500? That's what we're trying to figure out. Okay, so the first thing we're going to do here, we know our initial condition, so we're going to use our exponential model right here, okay? So we're going to say y is equal to, we know it's going to be equal to the initial condition, that's our y sub 0, which is 300 for this problem, times e to the kt power. Well, we can use our other ordered pair that they gave us, the fact that at time t equals 24 hours, the population is 1,000. We can use that information to solve for k. Okay, so we plug in 24 for t and we plug in 1,000 for y, and we get 1,000 is equal to 300 times e to the, you can either write k times 24, or I would obviously prefer 24k. okay? And then if we're trying to solve for k, we're going to need a log here, but the first thing we're going to do is we're going to divide both sides by 300. So this is just some algebra here, some algebra 2 back in those days. So 1,000 divided by 300, that's going to be 10/3. So we get 10/3 is equal to e to the 24k power. And then if we want to get that k out of the exponent, we're going to need to take the natural log of both sides of this equation. So the natural log of 10/3 is equal to the natural log of e to the 24k power. And again, we do that because the natural log of e, that just cancels out. So we end up with the natural log of 10/3 is equal to 24k, and then we divide both sides by 24. And we end up with k is equal to whatever ln of 10/3 divided by 24 is. And for right now, I'm just going to leave it in that form, okay? Because that is the most precise value of k. If I turn it into a decimal, I start rounding, and then my information is not as accurate anymore. Okay, so now that I know k, I'm ready to write a population model for this situation. Okay, my population model now looks like y equals 300 times e to the ln of 10/3 over 24 times t. And again, that's all in the exponent of that base of e. Okay, now I'm going to simplify this a little bit, okay? I'm going to say this is equal to y equals 300 times e, and I'm going to do the natural log of 10/3, that raised to the t over 24 power, okay? And again, that's just a little bit of algebra, right? Power to a power with exponents we multiply, right? So we can make it look like multiplication. We can just separate that out. And the reason that I want to do that is because what happens with my e and my natural log? Well, those are going to undo each other, right? So I really have y equals 300 times 10/3 to the t over 24 power. And that is just a little bit nicer to work with, so that's why I did that. So now we still have to answer the question, when is our population equal to 500? Okay, well, there's a couple of ways that we can do this. One way we could do this is to solve it graphically. We could take our graphing calculator and we could type in this function here, our population model, and then we could type in 500, which would just be a horizontal line, and we could calculate the intersection of those two. Okay, that is one way that we could solve this problem. But obviously the other way that we can solve this is algebraically by plugging in 500 for y and doing the math. So if I do that, I just need some extra space here, running out of room. So if I do that, I'm going to have 500 is equal to 300 times 10/3 raised to the t over 24 power. And again, I'm just trying to solve for t. I'm trying to figure out how much time it's going to take for that population to reach 500. First thing I'm going to do is divide both sides of the equal sign by 300. That's going to give me 5/3. So now I have 5/3 equals 10/3 to the t over 24 power. Next thing is I need to get that t out of the exponent. So in order to do that, I'm going to take the natural log of both sides. So natural log of 5/3 is equal to natural log of 10/3 to the t over 24 power. And then once I've done that, I can use my properties of logarithms and I can bring that t over 24 in front of the log. So I have ln of 5/3 is equal to t over 24 times ln of 10/3. Again, trying to solve for t, next thing I'm going to do is divide both sides by natural log of 10/3. And then I'm going to multiply both sides by 24 because t is being divided by. And again, we're going to multiply both sides by 24. So we end up with 24 times the natural log of 5/3 divided by the natural log of 10/3. And now is the point where I grab my calculator and I type that in, and I get that my t value is equal to rounded 10.18 hours. And you could certainly solve this by graphing as well. So let's take a quick look at that. I went ahead and I typed in the function in my y1. That's my exponential growth model. And I typed in the function, or the y equals 500, because we want to know when is the population equal to 500. I adjusted my window here. My x minimum is 0, my x max is 15, just because I know that the answer is 10.18, so I wanted that to be in my window. And if I'm looking at where these intersect and my population is 500, I want to make sure that I see that intersection, so I change my y min to 0 and my y max to 1,000. So then when I go ahead and I take a look at the graph, the blue is the exponential model, and the red is that horizontal line where the population is 500, and obviously I want to know where these two functions intersect each other. So I'm going to do a second level calculate intersect, and right there the calculator tells me that when y is 500, x is 10.18. That is the point that these two functions share. So basically just proof that my algebraic calculations were correct, and that the population will be 500 at 10.1 or after 10.18 hours. All right, moving on to example 2. E. coli is a bacteria found in human intestines. One cell of this bacteria divides into 2 cells every 20 minutes. The initial population of a culture of cells is 60 cells. Okay, so this right here, this is my initial value, right? But this is a little bit tricky because they tell us that our population doubles every 20 minutes, which we know is every 1/3 of an hour. So that means that after 1/3 of an hour, I would have had 120 cells, right? Because if I start with 60 and 20 minutes later it's doubled, that means after 1/3 of an hour, I have 120 cells. After 2/3 of an hour, it would double again. So I would have 240 cells. And after 1 hour, it will double again. So I would have 480 cells. They're asking us to find the relative growth rate in this problem. So basically what they're asking us to find for part A is our K value. So let's just start with our function, which we know is going to look like y equals why not times e to the k times t power. And we know that our y naught, or our initial quantity, is 60. And we can use, we've got 3 ordered pairs over here that we could use to solve for k. Why not use this one right here, because that one seems like the easiest one to work with. So that's the one I'm going to use. So y, I know, is going to be equal to 60 times e to the kt. And if I go ahead and I use the ordered pair 1, 480 to solve for k, I'm just going to go ahead and I'm going to plug 480 in for y. And I'm going to plug 1 in for t. Okay. And then I do the math. So if I divide by 60, I end up with 8 is equal to e to the k power. And if I want to get that k out of the exponent, I have to do the natural log of both sides of the equal sign. So I end up with k is going to be equal to the natural log of 8. So that's the answer to part A. That right there is my relative growth rate. So now part B wants us to find an expression for the number of cells after t hours. That just means write the exponential growth model, because we have the initial condition and now we've just solved for our k value, so we have everything that we need. this is our model, right? Y equals y naught times e to the kt. So now we just plug in our y naught and we plug in our k. And our answer for part B is going to be y is equal to 60 times e to the ln 8 times t. And you might want to put parentheses around that e to the ln 8, okay? Just to remind yourself that ln 8 and t are being multiplied. But again, we can separate that out, and we would want to because we can simplify e to the ln 8, right? That's going to just be 8 because the e and the ln cancel each other out. So really, my model simplifies to y equals 60 times 8 to the t power. So that is my answer to part B. Now we're going to use our model. Part C asks us to find the number of cells after 8 hours. So just plug in 8 for t. So y is going to be equal to 60 times 8 to the 8th power. You grab your calculator. It's a big number. Y is equal to 1,006, 632, 960 cells, right? 1,006,632,960 cells. That's the number of cells after 8 hours. Part D asks us to find the rate of growth after 8 hours. Okay, so now we're going to be thinking about this in terms of a differential, right? Because the rate of growth, that's going to be dy dt. And we know from our previous work today that dy dt is going to be equal to k times y, right? But if we want to find the rate of growth after 8 hours, okay, well then dy dt is going to be equal to, we have a k value, that's ln 8, and we have what y is, right? This is y right here. Hang on, let me switch colors so I can kind of illustrate that. This is y. Whoops, sorry. I went too far. I'm going to write it over here. My y is equal to 60 times 8 to the t power, right? There's my y. So I'm going to plug that in. Okay. And when I simplify that, grab my calculator, I'm doing natural log 8 times 60 times 8. Oh, and sorry, I shouldn't have put t here. I should have put 8, right? Because it's after 8 hours. So I just multiply those things together and I get dy dt is equal to, also a pretty big number here. Whoops, I'm going to write it below. It's to 2, 093, 234, 394. So 2,093,234,394. That is the rate of growth. That's the derivative at the time when t equals 8. That's our dy dt when t is 8. All right. And then part E, the last part of the problem, says, when will our population reach 20,000 cells? So again, you could do this on your graphing calculator, right? You could graph our function 60 times 8 to the t power. You could graph 20,000 and you could calculate the intersection. Or you could do it algebraically, which is what I'm about to do right now, which is 20,000 is equal to 60 times 8 to the t power. Okay, so doing the algebra, we're going to divide both sides by 60, and 20,000 divided by 60, again, I'm just going to try to keep things simplified until the very end, and then I'll grab my calculator so I get my most accurate answer. So this is going to be 1,000 over 3 is equal to 8 to the t power. And then I need to do the natural log of both sides. So natural log of 1,000 over 3 is equal to the natural log of 8 to the t power. So then the t can come down in front of the natural log, and I end up with t is equal to, when I divide both sides by natural log 8, I get natural log of 1,000 over 3 divided by natural log of 8. Now I grab my calculator and I type that in, and I get time is equal to 2.794 hours. And again, if you wanted to verify that, you could certainly graph it on your graphing calculator and prove that your graph intersects the horizontal line 20,000 at time t equals 2.794 hours. All right, so that's the end of example 2. In our last example, example 3, the quantity R in grams of a certain radioactive substance decreases according to the exponential decay model dr dt equals negative 0.05 R, where t is measured in seconds. During an experiment, a scientist determines that the rate of decay of a second substance with the quantity S in grams can be represented by a linear model ds dt equals -4, where t is measured in seconds. If at time t equals 0, R of 0 is 100 and S of 0 is 125, looks like they're giving us some initial conditions there. At what time t in seconds will there be equal quantities of both substances? All right, so let's start with the function R, which we know is an exponential decay model. So I'm going to switch ink colors here. So if we are given that dr dt in this problem is equal to negative 0.05 R, and we're also given the initial condition that R of 0 is equal to 100, we can go right from that information to our exponential decay model because we are smart calculus students. So we know that R of t is equal to my initial condition, which is 100, times e to the negative 0.05 t. There we go. Yep. All right. So there's my function for R of t. Okay, and then they tell us that we've got this other function, ds dt. Okay. And this is a linear model, right? Well, that makes sense because if the derivative is a constant, then the antiderivative had to be a linear function where t is measured in seconds, right? And they tell us here that S of 0 is equal to 125. Okay, well, if I integrate, sorry, I should separate first, my apologies. So ds is equal to -4 dt. Okay, there we go. Then S of t is going to be equal to -4t plus c, right? But if this is my initial condition, then that's my c value. So S of t is equal to -4t plus 125. All right, so now I have found my, my model for my exponential decay. That's my R of t. And I've found my S of t. So now if I want to determine when there will be equal quantities of both substances, you know, I could set these two equations equal to each other and I could solve algebraically, or I could grab my graphing calculator and I could solve with my graphing calculator. So I advocate for using the graphing calculator on this one, right? We found our models. Let's write what we did. Find models for S of t and R of t. Then graph to determine the intersection, okay, which is exactly what we're going to do. I've got my two functions typed in here, my exponential decay model and my linear model here, which is also a negative slope, right? And I adjusted my window. I went from 0 to 50 on the x scale, from 0 to 200 on the y scale, just because I know that my initial values for both functions are going to be 100 and 125, so I wanted to capture those. So then I go ahead and take a look at my graph. Again, the exponential decay, the R of X is, or R of T, excuse me, is the blue, and the S of T, the linear one, is the red. So now I want to go ahead and I want to calculate the intersection. And the calculator tells me that the intersection happens, remember X is T, right? So the intersection happens at T equals 23.548 seconds. 3 places here for the AP test. All right, so that's going to be the solution that I'm going to write down here on my paper. And then just for the sake of thoroughness, I'm going to sketch a little picture of what we just discussed here. My X scale went from 0 to 50, and my Y scale, I know that my exponential growth or decay begins at 100, and my linear function began at 125, right? So I had my R of T, which was my exponential function. That's looking kind of like this. And I had my linear function looking something like this. And we were calculating this point right there, which ended up being 23.548 seconds. And that's it, folks.